questions from 2.8?
I guess we gotta do this first.
Thanks, Omi. Giselle.
Could you do number 51? Yeah.
Sure. All right. So for part A, it says use equation 2.7.5 to find f prime of A. So that equation 2.7.5 was just the other limit definition, the one that we don't use as often. So if I plug this in, I'm going to have the cube root of x. I'm going to write as x to 1/3 minus the cube root of a. I'm going to just write that as a to the 1/3 over x minus a. I know! I forgot my limit. I got it. Okay, so that's that. So the reason that they requested that you write it this way is because it's going to make the simplification massively simpler than if you use the H definition for a limit. So the trick here is I want to look at x minus a and think about that as a difference of 2 cubes. So remember the difference of 2 cubes factoring pattern from Algebra 2 was this. So if I'm going to think about x to the first as a perfect cube and a as a perfect cube, I would think about it that way. So a minus b is going to be x to the 1/3 minus a to the 1/3. And then a squared is going to be x to the 1/3 squared plus a to the 1/3 x to the 1/3 plus a to the 1/3 squared. So that's the trick there that I'm going to use to make this simplification a little bit less unpleasant than it needs to be, or than it could have been. Because we see right there, once I've done this factoring, the numerator cancels on out of there with the problematic part of the denominator. So when I do my limit, I'm going to have a 1 on top, and I'll have an a to the 2/3 plus a to the 1/3 times x to the 1/3 plus a to the 2/3. When I simplify that, oops, that's not supposed to be an x anymore. I subbed an a in. I have a to the 2/3 plus a to the 2/3 plus a to the 2/3. So I have 3a to the 2/3. So far, so good? Mm-hmm. I know. Part B is easy, though, because f prime of 0 clearly undefined, right? Yeah. Okay, awesome. And part C says, show that the cube root of x has a vertical tangent at 0, 0. So I need to show that the slope of f of x is positive or negative infinity when x equals 0, right? That's the idea. So this tells me to use the derivative, and this is telling me as x approaches 0. So I go ahead and I reduce this, but I get something like over 0 here if I try to do direct substitution, right? So I could do like a table at this point. And you'll see that these y's head to infinity. And that would be enough to conclude that. I'm not going to punch those through just because I'm lazy. And I think you probably get the idea. Is that okay, Giselle?
Mm-hmm.
So you'd say like, so what we've done here is we've shown the slope of f of x at 0 is infinite, which is the equivalent of having a vertical tangent.
What? Did it just go to like x to the 1/3?
Why did it just go to... Oh, because f of x is the cube root of x, and f of 0 is 0 to the 1/3, which is just 0. Right? So I just, rather than writing minus 0, I just didn't write it. Is that okay? Right? So this is like x 1/3 minus 0 to 1/3. Oh, that was f of x in the problem. We're still talking about the same f of x the whole way through, right? That's still that same f of x. Sorry. Yeah, is that okay? So again, like, why did we have to do this part at the end? Is because that's our definition for a vertical asymptote. Is that the limit at the finite value goes to either positive or negative infinity from the left or the right, or just the limit in general. So technically, what did we do? We did the right hand, or the right hand limit, because I took values that were bigger than 0. Does that feel okay though? It's these old definitions that like are tough to remember because they all kind of run together a little bit. Make some flashcards though. Or if you want it, we can take some time in class and just like make a set of flashcards on a Quizlet or something and share it out. That's maybe not a bad use of time. You know what I mean? Other homework questions from anybody? This is the worst one, I thought. Or at least like technically the trickiest, because you really had to feel good about your definitions, and you had to use that factoring trick in the first part to get it to work out, which was not trivial to come up with. Like that's some sneaky factoring. It's like, oh, I'm thinking about x minus a is a difference of 2 cubes. Look at me, I'm fancy man. That's a sneaky pull to come up with on your own after not seeing it before. Okay. If there's nobody else, let's go ahead and start chapter 3. I'm going to make some friends here in chapter 3. So the first half of chapter 3 is all about shortcuts for derivatives. So the limit definition of a derivative goes bye-bye for the most part. What do you mean by for the most part, Mr. Kulik? Well, if I give you a function that's defined as a graph or a table, you can't really escape it then, but the shortcuts we're going to show you. If your function is defined as an equation, we're going to start working through the shortcuts and how to deal with that without having to use that limit definition, which is pretty tedious, right? Some of those limits were like a page to do. The same one-page problem is going to become a one-line problem. Ooh, you have my attention now, Mr. Kulik. All right, so our first derivative shortcut, the derivative of a constant, is 0. How do I prove that? I'll go back to the definition of a limit. F of x plus h, if f of x is c, it's just c. F of x is just c. C minus c is 0, limit is 0, 0. Ooh! Very nice. Should you memorize this? Yes. Okay. Oh no, I wanted to include a different one in here. I didn't. Apparently I did something dumb. Okay. Do that real quick. Make a space. Next one up, the derivative of x. Is 1. Should you memorize that?
Yes.
Yes. How do I prove it? Well, assume f of x is just x. We use our definition of a limit. I'm going to use the h definition. So f of x plus h is just x plus h. Boom, 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 boom. And we're done. Okay? So limit, or the derivative of x, just 1. The next one says, called the power rule. The derivative of x to the n, as long as n is a positive integer, is n times x to the n minus 1. Should you memorize this? Yes. How do we prove it? Same way. This one is just a bit messier. Oh, you know what? I'm not using that definition. I need to factor. This will be easier. I'm using that definition of a limit. So what is f of x going to be? Stupid Mr. Kulik. What is f of x? X to the n. What is f of a? A to the n, right? What's that numerator look like to you? Kind of looks like a difference of somethings, right? Whatever n is. So remember here, like if I have a difference of squares, you got that. If I had a difference of cubes, I'm going to have something like that, right? What's going to be the difference to the nth? I'm going to have the x minus a part out front, right? And that's the part that I really know that needs to come out so that they can reduce. But what else is going to be in there? Well, the leading thing decreases by 1 in the degree, right? I went from a to the third and went down to a squared. So my leading thing was x to the n, so that's going to go down to the n minus 1. and then I'm going to have 1a, and then that x is going to go down another one. So there's that. How many terms do you think I have here? Nope, not infinite, because you see it has an ending. Ooh, you're so close. Yeah. Degree 2, I had 2. Degree 3, I had 3. Degree n, I'm going to have n terms. So the point of that factoring was for that to happen, right? Now I'm going to do the limit. So everywhere there's an x, I'm going to put an a. Just doing a direct substitution. Oops. What do you notice that each of these terms comes out to be? They're all a to the n minus 1, right? And how many of them do we have? N of them. So I have n times a to the n minus 1. That's our proof. What was the hardest part? Doing the factoring, right? The factoring was non-trivial, but that's the pattern. Do you need to know how to prove it?
No.
No. Do you need to know how to use it?
Yeah.
Yes. All right, let's do some practices. If f of x is equal to x to the 6th, the derivative is 6x to the 5th, right? The exponent becomes the coefficient, and then we subtract 1 from the exponent. Think about how long that would have taken to do with the limit definition. Woof, right? Mr. Kulik, you would have had to expand out x plus h to the 6th. That doesn't sound like a lot of fun. B. Here, f of x is equal to x to the 1,000. How terrible would that be? Oh my God, right? Yeah. What's the derivative for it, though? The 1,000 becomes the coefficient, and the exponent you just subtract 1 from, and you're done. Whoa! Those one-page problems are like becoming a 3-second, one-line problem. What a time saver. C. T to the 4th. The derivative is 4t to the 3rd. Part D. R to the 3rd. The derivative is 3r squared. Notice in each of these we asked for the derivative using a different notation. Right? The first one asked for f prime. The second one wanted y prime. The third one wanted dy dt. The third one wanted you to do d dr of r cubed. They're all asking you to do the same thing. Just take the derivative. Remember we talked about there's lots of different notations that we inherited from all the disparate European locales where calculus was being done independent of one another. Those are the four most common notations. But the power rule gets better. It gets better. Because it doesn't work just for positive integers. It works for any number, or I should say any real number exponent. So it does negatives. It does fractions. It does irrational exponents. Like x to the pi. Do it all the same way. Wonderful, Mr. Kulik. Wonderful, because I couldn't even tell you what the heck I'm supposed to do with an x to the pi with the limit definition. I don't know what to do with that. Can't factor it. What am I going to do? Doesn't matter. Power rule will take care of it. Are we going to prove that? What do you think?
Yes.
No. This general rule? No. No, that's much too difficult for a course like this. We can do the positive exponent where all it really is a factoring problem. This one, it's like a real analysis. That's a deep theoretical question. All right. Let's do some more examples. F of x equals 1 over x squared. Mr. Kulik, that's a fraction. What rule am I supposed to use with that?
Like you can move it up. That's
Yeah. So remember this rule of exponents from Algebra 2? It's exactly what we want to do. We're going to think about that as x to the negative 2. So when you take the derivative, we get negative 2 x to the negative 3, or negative 2 over x cubed. Now, I wouldn't mark you down if you wrote this as negative 2x to negative 3. But if you look at the answer in the back of the book, or if you look at a multiple choice question, they will for sure write it as negative 2 over x cubed. They won't leave it with a negative exponent in it. I can almost guarantee that would be the case. So far, so good? Well, how about this next one, b? How am I supposed to do that, Mr. Kulik? I don't know how to deal with a radical. Yes. So we know that the nth root of, well, let's just say a to the m is a to the m over n. So we'll think about this as x to the 2/3. Again, that's another Algebra 2 rule. So when I take the derivative, I get 2/3 x to the 2/3 minus 1. So 2/3 x to the negative 1/3, or 2 over 3 cube roots of x. And again, I wouldn't mark you down if you wrote 2x to the negative 1/3. But if it's a multiple choice question, that's not probably going to be the choice. What I wrote down would probably be your choice. Almost guaranteed. Everybody's okay with how I got from 2/3 x to the negative 1/3 to that final one? The negative makes the x go in the denominator and the 1/3 makes the cube root. Isn't this nice? Think about how big of a pain some of these would be to do with that limit definition. But wait, there's more. Oh, not quite yet. I still have more though. Let's do this example. Find the equations of the tangent line and the normal line so normal just means perpendicular to the tangent. For the curve y equals x square root x at the point 1, 1. Illustrate that, we're not doing that part. Okay. If I want to write the equation for the tangent line and the normal line, what do I need? Slopes. What's going to give me a slope?
The tangent line isn't in that limit, but we shifted away.
I'm just going to use the derivative, right?
Okay.
Okay, so take the derivative of x square root x. How do I do that?
Use the power rule.
Yeah, but it's not written as a power yet.
X times x to the 1 over 2.
Yeah. Okay, and what's that simplify down to?
X to the 3 over 2.
Good. So my derivative then will be
3 over 2x to just 32x to the 1 half.
everybody cool with that? So this cool. And then y minus y1, m times x minus x1. There's the equation for my tangent line. What's the slope for the normal going to be? If it's perpendicular to the tangent, what? Negative reciprocal. Very good. So that would be negative 2/3. And then everything else is the same because it has to go through the same point. Boop. Did all this just get way faster? Way simpler? Well, I don't know about simple, but way less tedious for sure, right? All of a sudden, it's like, Mr. Kulik, that was like just a couple of lines and I'm done versus like a whole sheet where it was previously. Okay, next shortcut. If I have the derivative of a constant times a function, I can pull the constant out front and ignore it and just do the derivative of the part with the x's in it. Why do you suppose that works?
Factoring it out.
The distributed right.
Because the same property works for limits. And because a derivative is just a limit, I can use that same limit property to prove this. I'm not going to do that, but that's the idea. So remember we had this same property for limits where you can pull the constant out front of the limit. If a derivative is just a limit, it stands to reason I should be able to use that same property for the derivative. Okay, let's do some practices. What's the derivative of 3x to the 4th?
You can pull off the 3 first.
Just tell it to me. What's the answer?
3, like, derivative of x is 4.
Okay. I mean, I was like, good. I thought you'd just give me the whole answer.
Oh, and then you would pull in the 4, and then you would do 4 minus 1, which is 3.
Right? Everybody cool? All right, what's the next one?
Pull negative 1 out. Would it just be 1?
What? Yeah. The derivative of x is 1. That was one of our shortcuts that we did, the second shortcut we did. So just negative 1. Look at how nice this is. So far, everybody's happy? I think you'd be very happy with this. This is very nice. If f and g are both differentiable, then the derivative of a sum of two functions is just the derivative of each function independently. So essentially, the operation of differentiation is distributive. And that works for either addition or subtraction. Note that we have the same property for limits, right? If I take the limit of a sum or difference, I can distribute the limit across the sum or difference. That's why this works. It's because we have the same limit property, and a derivative is just a limit. Does everybody feel okay? This is really the payoff now. Look at this horrible, horrible thing. Imagine trying to use the limit definition on this. That's pages of calculation.
Probably pages. Like
Yeah,
20.
yeah. Well, I don't know about 20, but like, yeah, you're not doing it inside of a page unless you have like microscopic handwriting. Christian's like, I think I could do it. Probably, but you wouldn't be able to read it. That's the problem. All right. So, based on the previous two properties, we can just go piece by piece, right? Look at how wonderful this is. And like, do you even really need to show this work once you've gotten the hang of it? No, man, you can just go straight to writing down the answer. All right, what's the derivative of the first piece?
8x to the 7.
Excellent. The next piece?
48x to the 4.
Or 60x to the fourth?
Oh,
The next one?
16x to the 4.
Minus 16x to the third.
Plus 30x squared.
Great. Go ahead, you can shout them out together.
Minus 6. That's 5.
Nope.
0. Oh, 0.
Yeah, 0. Do you really need it then? No, you don't even need it. Look at that. Think about how long that would have taken using the limit definition. And that's something you could do in your head inside of 5 seconds once you get good at it. It's like an hour down to 5 seconds. That is a wonderful stinking shortcut, right? All right. Let's do a couple of examples. So it says find the points on the curve, y equals x to the fourth minus 6x squared plus 4, where the tangent line is horizontal. So when we say tangent line, what are we looking for? The derivative. And when the derivative is or the tangent line is horizontal, the derivative is equal to 0.
Because it's at a constant?
Because the slope is 0 when the tangent line is horizontal, right?
Yeah.
Right, a horizontal line has 0 slope.
Yeah.
Algebra 1, pre-algebra maybe,
Yes.
long time ago. All right, well, what's y prime going to be? Who can tell me?
You can use the rules.
Yeah.
4x to the third
Yeah.
minus
12x.
12, yeah. X to the what?
Uh-huh.
Just 12x.
Plus 4.
Plus 0.
There's still 0.
Mm-hmm.
Confusing on the limit.
And then I'm going to set that equal to 0. To solve that, I'll just factor. So I can take out a 4x. I apply the 0 product property. So I get x equals 0, and then plus or minus the square root of 3. So my points are 0. Where am I plugging that 0 back into? Y or y prime?
Y prime.
No, y.
I thought it was Y, but then you didn't say anything, so I already.
Well, because you slowed down. I was like, what's he going to say here? Is he going to end it, or is he going to say the prime? Points on the curve, they need to be on y, right? So 0, when I plug that in, I get 4. Square root x, or square root 3, that's 9. That's 3. 9 minus 18 is negative 9 plus 4 is negative 5. And then since all the exponents were even, the negative root is going to give us the same thing. So those are our 3 points.
It's impressive you could do that in your head.
You could do it too. You just needed more practice. That's all. Again, you guys are better math students than I was at the same age. The difference is 20 years of practice is a big separator, right? All right. The equation of motion of a particle is S equals 2t cubed minus 5t squared plus 3t plus 4, where S is measured in centimeters and t in seconds. Find the acceleration as a function of time. And then what is the acceleration after 2 seconds? So I want a of t, and then I want a of 2. How do I do this? Physics students?
Acceleration is slope of velocity.
Which is,
The derivative of velocity.
okay, and velocity is the,
Derivative of position.
okay, so this is the second derivative of position.
Yes.
Everybody's cool? All right, well, let's find S prime first. What's that going to be? You guys agree?
Yeah.
And then S double prime then would be? Everybody happy? Look at how fast that was. It did 2 derivatives in like 10 seconds. Boom, boom. Now, I know you're not quite as fast as this yet, but you'll get there. It won't take too long. This is an easy rule to execute. It's very mental math friendly because all you're doing is like whole number multiplications and additions and subtractions. Like, we can do this. So far, so good? Questions so far? Everybody all right? Okay. This next definition, I've seen one time in the AP question bank. That's it. It's something you should treat as like just a like identity, like a fact. I don't think it's really that important, but I'm going to put it on here because I've seen it used once in an AP problem that I've looked at. I've looked at a lot of AP problems in the course of teaching, getting ready to teach this course. Gone through and done lots and lots of them. One time I've seen this come up, and I think it was probably not an AP generated question, but rather somebody added it to the question bank. But that's is in our textbook, so I thought I would mention it. This one, though, absolutely must have memorized. The derivative of e to the x is e to the x. Won't prove that here. Again, that's pretty tricky. Like you'll end up having to use that limit that I just gave you to kind of make that work. Here's a question for you then. What's the derivative of e squared?
0.
0 is correct. Why, Nolan?
E squared would just end up being a constant number.
E squared is a constant. E is not a variable, it's a number. A number squared is just a constant. The derivative of any constant is 0. Yes, don't be fooled by this. The AP loves doing things like this and putting things that don't look like a constant and making them like having it be a constant to try to trick you. But that's it for today. How was this? Like, how lovely was today? Like, are there kind of a lot of problems here? Sure, but guess what? They're fast. You should be able to do them fast. Yes, Chanel.
So for the bolded ones, you want us to do 23 odd?
Uh-huh.
For the bolded ones? Okay.
Mm-hmm. Yeah, so I tried to make that as obvious as I could. That like I wanted, those are all the odd ones, or the bolded ones are just through there odd, because notice 25, 27, 29, and then 29 through 35 are all not 13 to 35 odd.
Okay.
It's like specific, you know what I mean?
Oh,
Like I broke that up in such a way that like hopefully it was super clear.
oh, so you're saying like 13 to 35 odd, but for the homework was 13 to 23 odd?
And then 27, yes. Yeah. So next time, we're going to look at two other derivative shortcuts to deal with if you have the product of two distinct functions that you can't combine into a single thing. Like we had x times the square root of x, but we just wrote that as x to the 3/2. But if I had x times e to the x, there's no simplifying I can do on that. I need a new derivative shortcut to handle something like that. And similarly, if I have x divided by the square root of x, well, I can simplify that. That just turns into the square root of x. But if I had e to the x divided by x, there's no simplification shortcut for that. We're going to learn that shortcut then next time. Yes, Tony.
Will we have to use like any of the limit derivative stuff on the test, or can we just use the stuff?
I'm still in the process of writing what I have for the test. What I would say to you is like the place where the limit derivatives you're not going to be able to get away from is if your function is given to you as a graph or like a table. You still kind of need that information or that idea to be able to cope with those situations. But if it's given to you as an equation, unless you're specifically asked to like show this limit or this derivative is this using the definition of the derivative, no, don't do the limit. Do these shortcuts. You know, because why would you? You wouldn't. Nobody wants you to do that. I don't want to do it. This 2.7 and 2.8 are my least favorite sections the whole year because it's just like feels like I'm pounding my head against the wall for no reason. But like, there's a reason. Like, we need to do this so that it makes the shortcuts make sense. But Chanel.
Can I borrow a textbook from my cabinet? My textbook's at home.
Absolutely, yeah, for sure. That's it for today, though, guys. Isn't this lovely? Like, does this feel easier than last chapter so far? I know some of the stuff in the previous section was tedious, but like the tedious stuff I'm not going to ask you to do on the test, right? It'll be like, you know, here's a graph. Where does the derivative fail to exist? You know, like that kind of like the conceptual stuff from those sections is still really important. But like, do the derivative with the limit. Like, I'm not gonna ask you to do that. You know what I mean? Because just yuckers. Stop this recording. You guys asked a lot less.